because radical substitution. So again, we mainly focus on bromination because we know chlorination is not regioselective. Um, so radical substitution, the mechanism is a radical mechanism, uh, having an initiation step is where radicals are formed, then propagation, and propagation always is two steps, and it's cyclic. So basically, a radical forms another radical, another radicals react with a molecule from another radical, which is what you need for the step one. So it's a cyclic process. And then once this goes over millions of times, you got termination, which is when two radicals are formed. And then that's the end of the mechanism, right? So we talk about bromination mostly because the slowest step for bromination is endothermic. So very quickly, so remember, so step one, maybe this might help to whoever was asking this at the very beginning. Um,
Sorry, Professor, I actually have a question regarding this.
mhm.
Are you expecting us to show initial propagation and terminal when if we're ever to be given a problem like that, or are you just expecting us to show the reaction?
No, you need to know the mechanism. You need to know the
Oh,
mechanism. Mhm.
okay.
So initiation is formation of radicals. So you get two bromine radicals being formed. Um, two bromine radicals being formed. And that's what kicks the reaction up. Remember, you just need a few radicals to be formed for the reaction to trigger. Uh, just a few bromine molecules will be forming bromine radicals. Um, and once you got the bromine radical, then you got propagation. Propagation in step one, you got now the bromine radical reacting with the alkane. And this is what I discussed in class, why bromination is regioselective. So remember, the hydrogen taken away here by the collision with the radical is going to be that hydrogen forming the most stable radical, right? And radical stability follows the same pattern as carbocation stability because they are both electron deficient species, right? So tertiary radicals are more stable than secondary radicals and primary. Obviously, we got tertiary benzylic and tertiary allylic, which are the most stable of all of them. So in a case like this, you're gonna have obviously the tertiary radical reacting here with the bromine, and that's gonna lead to a molecule of hydrobromic acid and a molecule of an alkyl radical. So the drawing here is not as perfect because I'm not using obviously the board and classes a lot easier to be using this program that is nice, but it's not that easy for half hours. So that will be forming once again the tertiary radical is the most stable in a molecule like this because once again radical stability follows the same pattern as carbocation stability. So same factors, hyperconjugation, inductive effect, and resonance are the factors. So a molecule of hydrobromic acid is formed. And then in step two, the alkyl radical will be reacting now with a molecule of bromine, and that will be forming the heteralkane plus another bromine radical, which is what we need in step one for the reaction to continue going on forever. So So you got here formation of an alkyl radical. And I'm sorry, the bromoalkane plus another bromine radical, which is, as I said, the reacting species in step number 1. So this go over and over again, right? So that's the mechanism for radical substitution. So this is a slow step, guys. This step in bromination, remember, slow step is here. In bromination, is endothermic, and that makes the reaction regioselective. In chlorination is exothermic, and that's why chlorination is not regioselective. So that's why we use primarily bromination for synthesis and never chlorination. So yeah, so you just need to keep track of stereochemistry. Let's say we had a compound like this. Well, if we were to have any stereochemistry here, since I don't want to, I'm not gonna add anything in this one. Well, let me give you another example because this is gonna complicate things. So let's say we were to have something like this. Simple. So the radical substitution will be happening at the secondary carbon for the same reasons. That would be the most stable radical. Same mechanism as I have here, but just with this alkane. So in that case, you will be having a new chiral center in the final molecule. Radicals are sp2 hybridized. And because radicals are sp2 hybridized, they are planar. So if you happen to be creating a chiral center in a radical substitution, you will always end up with a racemic mixture because both the radical can be approached by both top and bottom face of the p orbital. Okay, so keep stereochemistry in mind if you need to. The second thing that we discussed in class for radical reactions was the allylic substitution, very important. I'm gonna give you a couple of examples here. Allylic substitution is done with MBS. The reason for that is because, by the way, I need to add here light, because we want to avoid the competition with bromine adding to the double bond. We don't want that. That's an electrophilic addition reaction that we don't want. So we want to force a radical mechanism. So in that case, we are adding MBS because it's a way of adding bromine slowly into the reaction media. Remember, and this is in the textbook as well, I discussed the mechanism in class. With MBS, you form a bromine radical, and after one molecule of hydrobromic acid is formed, this hydrobromic acid is reacting with MBS, and that's what will be creating bromine. So bromine is created very slowly in the reaction, and then what happens is that you got the substitution in the allylic hydrogen. So keep that in mind. In the case like this, once again, you're getting a chiral center to get a racemic mixture of both allylic substitutions. Guys, when you're doing the mechanism for this, you need to draw the resonance structures of both allylic radicals to show why both potentially two products are formed. In this case, you only get one because this is a symmetric allylic radical, okay? So this is just example with a linear and a cyclic alkene for the allylic substitution. I gave you problems to practice. You got plenty of examples to practice this at home. So allylic substitutions with MBS are highly handy for synthesis problems, so keep that in mind, please. So this is a reaction that you guys need to know. And the last reaction that we learned in class in regards to radical reactions was radical addition of hydrobromic acid to double bonds. Once again, a radical mechanism. We discussed it in classes in the textbook. So it's when we have hydrobromic acid and peroxides. So in that case, once again, peroxides are forming radicals. The radicals of peroxide reacting with hydrobromic acid and creating a bromine radical, which is what reacts with the double bond. once mechanisms in the textbook if you have questions about it. The end result of this is the bromine adding to the lowest substituted carbon. Again, if you happen to be having chiral centers in the final product, keep in mind that that's going to be something to keep in mind. So the bromine is ending in the lowest substituted carbon. This, I wasn't, I mean, I didn't pick a really good example here. I'm going to complete it because it's highly complicated. I'll tell you why now. So we are creating here two chiral centers instead of one. So this is a more complex problem than usual. So I'm completing the whole thing just to not leave anything recorded here with a mistake, but rarely you're gonna find such a complex example. So I'm just giving all stereoisomers in both cases. So the bottom line is, you got the bromine in the lowest substituted carbon of the double bond, okay? And that's the whole point. Stereochemistry, if you happen to be creating a chiral center, once again, you get a racemic mixture. In this case, you get a racemic mixture with two methyls on the bottom and two methyls on top. Same thing because, once again, the alkane is trigonoplanar and you got two substitutions. So slightly more complex than usual. If this is a little too complicated for you, I'm going to give you another easiest example here. What? So you want to do the radical substitution of this. This is going to be better. Once again, radical addition of hydrobromic acid. The bromine will end in the lowest substituted carbon. So it's opposite regioselectivity to that of the traditional polar mechanism that goes through a carbocation. This goes through a radical and that leads to opposite regioselectivity. Okay, so this reaction also quite useful for synthesis purposes. We use it in synthesis quite a few times. So for radical reactions, what you guys need to know is once again radical substitution, which is regioselective, only bromination, only the highest substituted carbon is a reactant. Keep track of stereochemistry. Reaction propagation, step 2 steps. The bromine radical reacting forming an alkyl radical, the alkyl radical creating another bromine radical, and so forth. Allylic radical substitution with NBS that reacts in the allylic hydrogens. And radical addition of hydrobromic acid to double bonds, opposite regioselectivity to the one that we studied before. So let me see questions here on the chat. Any specific questions in regard to radical reactions?